this is something I should have done before, and I am sorry I haven't done it earlier. It's a slightly more general version of the factor theorem. It's a little bit, it's a little bit more general, which makes it easier to use. Well, not easier, but makes it more, what's the word, applicable, so to say. Basically, we have this. From the division algorithm, if you remember, if you take a polynomial capital F of x and divide it by another polynomial d of x, what you'll get is by dividing, you'll get a quotient and remainder, essentially, right? That's what the division algorithm says. In particular, if we have a non-zero constant a and a number b, they're constants, and if we take d of x to be a times x minus b, and we're dividing capital F by that, then by the division algorithm, there'll be two unique polynomials, q of x and r of x. Q of x, of course, is the quotient. R of x, remember, is the remainder. Here, its degree, it's either going to be 0 or its degree must be less than 1. Right? The degree is always less than the degree of d, capital D, that is, the divisor. And in this case, capital D has degree 1. So capital R of x, the remainder, it's either 0 always, or its degree is 0. Either way, it's going to be a constant, is what we're saying. So I'm going to call C that constant. I'm going to let C be that constant. So in other words, we get this. But remember, we were able to figure out when the A was 1, although I think I called B A if I remember correctly, but when I first showed you the factor theorem, this actually was that's right. When I first showed you the remainder theorem, we were able to figure out that constant. And as you can see here, we can still do that. And why is that? Well, notice that if I replace x by b over a, remember, a is not 0, so this is okay to do. What happens is, when I plug it in to this equation, to both sides, we'll get this. And hopefully you can see that the a's cancel, but hopefully now it'll be easier to see. These a's will cancel. You'll be left with b minus b times capital Q at b over a plus c. C is essentially that remainder. Now, I don't know what Q is at b over a, but it really doesn't matter. Namely, b minus b is 0, and 0 times anything is 0. So we're going to get that c back. In other words, what I'm saying is this remainder c, we can actually calculate. It's equal to this. And altogether, what we get is a so-called, I guess, a more general remainder theorem here. Before we handled the case when you divided by x minus something, here I'm handling it now a times x minus something, ax minus b. Okay, well, of course, this isn't the factor theorem. If anything, this is a remainder theorem. We can use this, though, as here, right? Because this tells us that capital F of x has a times x minus b as a factor, right? If and only if the remainder is 0. But since we know what the remainder is, this thing, so it's going to be a factor if and only if f of b over a is 0. This is actually the original version of the factor theorem I showed you. This one's a little bit better because it's more applicable. You can use it on more situations, so to say. Basically here, we got this when a was equal to 1. Here, this is the case when we still have degree 1, but now we have b over a. where the coefficient of x here is not necessarily 1. So we can use this factor theorem. Okay, so we have this factor theorem, which is also really good, and we can use it, as you'll see today. Remember, we were in this example last time. Now, if I remember correctly, what we got up to was the LCD, right? We got the LCD to be this thing. Okay, so we know that's the LCD. So remember, we want to add these, right? Well, we have to have a common denominator, just like fractions of integers. And this is our common denominator, the LCD. So we have to rewrite each expression here, rational expression, excuse me, as such. We have to rewrite it so that the denominator becomes this. So for instance, for the first one here, what do? Well, we're going to multiply. So we want the denominator to become this product, the LCD. Notice we're missing 6 times x minus 1. Okay? 6 times x minus 1 we're missing. Okay, so we got to multiply the denominator by that, the bottom that is. But remember, whatever you do to the bottom, you do to the top. Got to keep it, you have to keep everything algebraically the same. Okay, so in other words, this becomes this, which is nice. Okay, that's what we get. All right, same thing for the second rational expression. Although here I factored the denominator, right, as you can see. Because now it's easy to see that the only thing we're really missing is a 6x plus 1, right? The LCD is 6x plus 1 squared times 6x minus 1. Down here, though, we only have one 6x plus 1, right? We need another one. So I multiply the bottom by that. And again, same thing. What you do to the bottom, you do to the top. And we get this wonderful thing. Yahoo! So this is what we get. Okay? So these two we have, they're both equal. I mean, they're both equal, sorry. We have this is equal to this here. This is equal to this. The denominators are the same. Now we can add them. And when we add them, we just combine numerators. But since we want to simplify, we do have to carry out these products on top. Okay? Here it's not obvious if the numerator and denominator have any common factors, okay? It's not obvious at first. So, we want to simplify it. So we have to carry out these products on top. And that's how I get from here to here, right? We FOIL. So here we get 12x, excuse me. We get 12x squared. 12x minus 2x times negative 1 is minus 2x. 1 times 6x is plus 6x. 1 times negative 1 is minus 1. Here we have x times 6x, 6x squared. We have x. 2 times 6x is 12x. 2 times 1 is 2. So we get all this. And of course, we combine like terms in the numerator, right? That's how I get here. Right? We have 12x squared, 6x squared. That's 18x squared. Minus 2x plus 6x plus x and 12x, right? They're all like terms. We're going to combine those terms. We have minus 1 and 2. And then we get this. Okay. And when we do that, we end up with this. So this is our sum. We're not quite done, though, because we want to simplify. Right? We want to know, does the numerator and denominator have any common factors? And again, right, what you can do is you could try factoring the numerator. You could do that. Okay? But instead, let's use our factor theorem. Right? This is the factor theorem from before. I just showed you. Okay. Okay, and this is our f of x here. And we basically want to know if 6x plus 1, 6x minus 1, if they're factors of f of x, right? That's really what we're after. So it's enough to check if f at, if we have to determine what the roots, well, I shouldn't say that. So let's handle each factor individually. Okay, sorry, I lost my train of thought for a second. Sorry about that. So for 6x minus 1, we want to know if that's a factor, right? Well, according to the factor theorem, it's enough to check if 1 over 6 is a solution, if 1 over 6 is a root of the numerator, is a 0 of it, that's better. Right? You can see just by comparing, we could take a to be 6, b to be 1. It's enough to check if f at b over 1, or in this case, 1 over 6 is 0, if f of that is 0. And that's what I'm checking here. I'm checking to see if this is true, right? And that's what I'm doing here. Right? As you can see, we have b is 1, a is 6, and it turns out we don't get 0. So this is not true, is what we're saying. So 6x minus 1 cannot be a factor of the numerator, which is our f of x. We could do the same thing for 6x plus 1, but notice here we have a minus, right? We have to have subtraction. That's why I rewrote this as 6x minus minus 1. That's why I wrote it like that. So in this case, we're going to use this, but we have our b is negative 1, and our a is still 6. That's what we're doing. And again, if you do that, you get f of this turns out to not be 0. So this is also not a factor. Well, if 6x minus 1 and 6x plus 1 are not factors of the numerator, that means this is simplified and there's nothing else to do with this example. All right, are there any questions on this? I know I did lose my train of thought while talking because I was trying to, really explain it well. But again, I am sorry about that. Yes.
So when you did the 6x plus 1,
right.
How did you get negative 1?
Because we want this to be ax minus b. Here we have 6x plus 1. We want to write it as subtraction, but we can do that because addition is minus the negative.
So we put that in as an, why are there two negatives though?
Because we want this to be subtraction, but we have addition. We can make addition into subtraction by writing it as minus the negative.
Oh, okay.
Okay.
All right.
Does
Thank
that make
you.
sense?
Yeah.
Okay. Again, if that doesn't make sense, if something doesn't make sense, whatever it is, please speak up. I really hope this makes sense, because if you did try because if you have addition here, if you have addition here, you have to make it into subtraction. Otherwise, this theorem doesn't apply directly. You have to do something like this. Okay. Sorry about that. I don't know what happened. I got kicked out of my own classroom. What a world. All right, let me just